Welcome back to part 6 in the series on loops. In this video, we'll go ahead and do some exercises to get more practice. First of all, we're going to write a whole bunch of code snippets to perform various loops. I've repeated the exercises here. First, let's print a list of even integers, 0 to n, 1 to a line. First of all, we'll need to establish the variable n. We can reset it later. We'll also need an iterator variable. Now it's more natural to do a for loop here because we know exactly how many iterations we're going to be doing up front. We can check to see if it's even by using the integer division operator. If the remainder is 0 after dividing by 2, then it's even, and we'll print it. Simpler code is always better. If we could get rid of this if statement, then it would simplify our code. In fact, we can do that by, instead of going up by increments of 1, go up by increments of 2. Let's also test that it works for different values of n. Even better. What happens if we increase the value to 21? It doesn't change. That's because of how we defined our continuation condition. Let's print out the same list, but instead of end lines, we'll print out commas. Kind of messy. We delimited it by commas, but we'll probably want to add a space as well. Not only that, it didn't end the line after the list. Let's fix both of those things now. A little bit better, but we still have that trailing comma. It's common to have to deal with the first or last iteration separately outside of the loop. We'll do that here. The formatting issue is solved, but now we've got a different problem. Because we're handling the last loop separately, we have to change our logic. We could surround our last print statement with an if conditional to check to see if I is still within the range that we want. Or, even simpler, we could restore our old logic, but subtract 2 to ensure that the loop terminates one iteration that it did before. And now it works. Even if we change the value. Now let's print a list of integers divisible by 3 between 10 and 100 with a total as well. We'll need another variable. Don't forget to initialize it to 0. We'll use another for loop here because, again, it's more natural. We know up front how many iterations we're going to be executing. Now if we start at 10, we know that that's not divisible by 3. The first integer between 10 and 100 that's divisible by 3 is 12, so we might as well start there. The last integer that's divisible by 3 is 99, so we might as well stop there and increment in values of 3. We'll add I to the total using our compound increment and assignment operator, and we'll print it out. At the end, let's print out the total. You could probably do some clever math to verify that this is correct. Now let's print out all positive powers of 2. 1, 2, 4, 8, 16, up to 2 to the 30th. There are lots of different ways that we could do this. I know that I want to print out exponents 0, 1, 2, etc. up to 30. So let's go ahead and use our iterator variable to do that. Here we're using the math library, so I'm going to have to bring it in. Let's test it out. It works, but is there a way that we can simplify this without having to use the math library? We're only multiplying by 2 each time. So if I create a variable, start it out at 1, and then multiply it by 2 each time, that'll effectively double it. 1, 2, 4, 8, all the way up to 2 to the 30th. Here we've got an off by 1 error. 2 to the 0 is not 2. That's because we multiplied by 2 to begin with. We'll instead print it out and then multiply it by 2, so that we're not off by 1. And now it works without the math library. This is also more efficient, as the pow function is probably using some numerical interpolation method to compute powers. What happens if we go one more iteration, 2 to the 31st? We get a negative value. This is a classic overflow problem. 2 to the 31st is one more than we can represent using a 32-bit 2's complement signed integer. So it wraps back around to negative values. Now let's print all even integers, 2 through 200, on 10 different lines. That is 10 numbers to a line. We'll use the same trick as before, and increment by 2's. This will print out all 100 numbers on the same line. What we need to do is every 10th number, we need to print an endline character. Let's see what this produces. And it seems to work. I divided by 20, knowing that the 10th number would actually be 20 since I'm going up by values of 2. Here's another trick. Since the largest value that we're printing is only 3 digits, we'll go ahead and pad out all the numbers by 3 digits. And now everything is nicely aligned to the right. As our last exercise, let's print the pattern of numbers that was indicated before. This will be similar to what we just did, but it'll be more helpful to have a nested loop. We've introduced another variable here, j, which we'll have to declare. As per the hint, we'll use I plus 10 times j. Let's see what this produces. We're almost there. The numbers match up, but again we want 10 per line. To achieve that, we'll simply print an endline character at the end of the inner for loop. Again, we also have trailing commas. A trick to take care of that would be to simply handle the last iteration of the inner for loop separately. Now let's write a classic FizzBuzz program. This type of question is a common technical interview question. The task is to simply print out numbers 1 to 100, but for numbers that are multiples of 3, print fizz instead of the number. For numbers that are multiples of 5, print buzz instead. For numbers that are multiples of both 3 and 5, print FizzBuzz. Let's create an iterator variable. And since we know how many iterations we'll be doing, a for loop is most natural. Now the tricky part here is figuring out the logic. Recall from conditionals, the most specific condition should come first. In this case, it's when it's divisible by 3 and 5. The more general conditions are when it's divisible by just 3 or 5. And the catch-all condition will be to simply print out the number. And it works. 15, 30, 45, and other increments of 15 will print out FizzBuzz. 3, 6, 9, and increments of 3 will print out fizz. You can verify the rest on your own. One small optimization that I would make, though, is that an integer is divisible by 3 and 5 if and only if it's also divisible by 15. So we can greatly simplify this first statement and get the same results. Here's a more math-oriented exercise. Let's implement a program to use the Babylonian method to compute the square root of a number a using the following series. We'll start the series at x of 0 equals 1. Then each subsequent value will be 1/2 times the sum of the previous value plus a over the previous value. To understand that, let's look at an example. We want to compute the square root of 2. So in this case, a is equal to 2. The second term in the series is going to be 1/2 times the first term plus a over the first term. Since the first term is 1, we get 1.5. The next value in the series will be 1/2 times the previous value plus a over the previous value, which in this case is 1.5. And we're already quickly converging to the square root of 2. We'll stop when the current value that we've computed so far is only slightly different from the previous value. That is when the difference of x of n minus the previous value, x of n minus 1, is less than some small constant epsilon, which we can then tune. For now, we'll go ahead and hard-code the value that we want to compute the square root of. Let's also define a small epsilon. We'll stop our algorithm when it's accurate to within 1/100,000th. Now, we don't need to keep track of the entire series. We only need to keep track really of two variables, the current value and the previous value. We also don't know how many iterations we'll be doing up front, so it's more natural to use a while loop in this case. while the absolute value of the difference between the current value and the previous value is greater than or equal to epsilon, we'll go at least one more iteration. Our current value is simply equal to 0.5 times the previous value plus a divided by the previous value. Let's go ahead and give it a try. That didn't get us anywhere. We're actually forgetting two things here. We've got our continuation condition, but one thing that we overlooked was the initialization. We need to ensure that this while loop will actually execute at least once. Since it involves both the current and the previous value, we need to initialize those to something such that their difference is greater than or equal to epsilon. Now it'll execute at least once. In fact, it'll execute an infinite number of times. The problem again was that we were forgetting our increment statement. With this while loop, we don't really increment a number. Instead, what we need to do is we need to set ourselves up for the next iteration. We have two values here, current and previous. We need to make sure that we're updating both of those things. Basically, we're moving the value along. The previous will take on the current value, then we update the current value to the next value. Let's try that out. Our increment condition now interferes with our initialization condition. At line 12 on the first iteration, previous takes on a value of 0. So when we go to divide it, we get an invalid result. Let's go ahead and switch these two. And now we're getting at least something close. To see how close we are, let's go ahead and use the math library square root function as well. In fact, it's spot on. Let's print out more digits. And let's align them so that we can easily compare them. It's certainly accurate to within 1/100,000th. But in the least significant digits, they start to disagree. Let's make our epsilon even smaller. And now they agree out to 15 decimal points. So would you accept a job with the following conditions? You only get paid $1 a month. However, each month your pay doubles, but your contract only lasts for 2 years. Let's write a program to project our earnings under these conditions. Let's create an integer variable to store our monthly salary, which we start at $1. We'll use a variable called month as our iterator variable because that's what it's modeling. A 2-year contract lasts for 24 months. We'll also need a total salary. Let's print out everything that's relevant. The month, the monthly salary for that month, and a running total of how much we've earned so far. Now, if we ran it as is, the only thing that would actually change is month. We're not doing any updates to the monthly salary or to the total salary. Let's do that before the print statement. Each month our monthly salary doubles. And our total salary is updated with that month's salary. Let's make the output look nice as well, with headers. We're off by 1 here. In the first month, we get paid $1, not 2. Our mistake was doubling the monthly salary before taking a total. Now in the first month, we earn $1, and our total is only $1. In the second month, we earn $2, and our total so far is $3. In the third month, we only earn $4, and for the last 3 months, we've only been earning $7. But by the 24th month, our total salary comes to $16 million. So do you take that job? We can clean up the output a little bit by adding dollar signs and aligning the header. Let's see what that looks like. Using tabs can be problematic. Let's instead use the formatting that printf gives us. Now everything is nicely aligned to the right, like a ledger book. I'll leave this last exercise for you. Dogecoin is exploding. It increases in value 20% every week. So suppose that we started out with 1,000 Dogecoins, which is initially worth $10. So in other words, 1 Dogecoin is equal to 1 cent. Let's take the following investment strategy. At the end of each week, we'll sell half of our gains and keep the rest growing. Then at the end of the year, we'll report how much cash we have, how much Dogecoin we have, and how much that is in total US dollars. Go ahead and have fun with this one.